This is for my students in calculus, and it's about how to sketch derivatives from function sketches. We did this in class, and I think I can give a nice little review for you guys. All right, so first of all, you might end up with a curve that, let's say you have a cubic of some sort. But it's not necessarily a cubic, but it looks cubic-like. So let's say we have this f function, and then I'm going to just, in green, I'm going to make the derivative of f. So first of all, I look for wherever my little car is flat. And wherever it is, I'm going to put an x on the axis. Now, between what I'm going to call A and B, between point A and B, the car is going downhill. So since the car is going downhill, I just connect the dots. Just make a little smiley face between A and B. And the car leading up to A, you see, is going uphill. So I just go flick. And the car after B is going uphill, so I just go flip, like that. And that's all I do. And we do happen to know, this is a peek ahead, let's say we know that f is approximately the shape of x cubed. It's not x cubed, but it's that shape. We kind of expect the derivative to have the shape of x squared. And that's kind of what we're getting. So it doesn't have to be an actual polynomial. It's just that we expect that sort of behavior. Let's do another example here. So we know that polynomials, for polynomials, the derivative reduces the numbers of wiggles. So let's try another function. Let's try what happens. So we have, what degree polynomial might this be? It might be 1, 2, 3, 4, 5. Hopefully you can see my pencil. Just in case you can't, I'm going to trace over it with a different color. 1, 2, 3, 4, 5. Every time I turn around, I count up one more time. So we expect the derivative might kind of look like an order 4 polynomial. Again, wherever the little car is flat, you make an x. And then the car is going downhill from A to B. The car is going downhill from C to D, but it's going uphill from B to C. And then again, it's going uphill from D onward, and it's going uphill from A before A. So this is what f prime would look like, again, roughly. Now, as a warning, I want to point out that what we do artistically does not always match what we're doing with the math. So for example, when I draw a parabola, I very often draw like a happy face shape, and essentially it kind of looks like a straight line here and here. And I'm going to let my computer do this. I'm going to let my computer make this into a straight line just to stress a point. This is a perfectly good parabola sketch, but it isn't actually a parabola. So let me explain what's going on here. The little car is flat over here, so I put an x, and let's see, this function is increasing, so it's going to look kind of like that. That's a perfectly good artistic graph of a parabola and a line. But what is actually happening, if I were to take this at face value, this piece of line segment here is, let's say, has a slope maybe something like up here, but it's flat. And this piece of line segment over here is down slope of about the same, so maybe it's kind of going like that. And somehow we have to connect these guys. So maybe it looks kind of like this, right? That is not a straight line. This guy, f prime, is a good approximation of what the derivative looks like, but that's not what we do. Okay, so what does it? This is a matter of understanding what the picture is trying to say, even though it's not being explicit about what it means. And so part of what we're doing in calculus is learning to interpret sort of the culture behind these pictures. The problem with parabolas is that it's really kind of impossible to draw a parabola. And I'm going to say why. Because a parabola, if you zoom way, 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 way out, it's going to look like that. You're eventually going to get these two parallel lines. It's going to look like two parallel lines. But wait a minute, they can't be two parallel lines, right? Because we know that as x goes infinite, y goes infinite. So we kind of draw the parabola at an angle. We draw the thing like it's going off at some kind of angle. And it doesn't really make sense because it's not going off at an angle. It keeps getting steeper and steeper and steeper and steeper. And if it were going off on a line, it would be a hyperbola, but it's not a hyperbola, it's a parabola. And so this is the kind of problem we are encountering. We can't capture the two competing properties of a parabola in one picture. We can't capture the fact that they kind of end up looking like parallel vertical lines, but they don't. They do and they don't. And that's kind of an enigma there. And so we can't draw both of those properties at the same time. And so we pick one and it's misleading in some way. Okay, so I want to talk about asymptotes, but I'm going to lead up to them. So if we have a sine or cosine type function, then we can go ahead and take the derivative, and what do we get? Okay, between a and b, the car is going uphill, so this is positive, and then between b and c it's downhill, so it's negative, and we just keep going like this. All right, this is just going in and out, in and out, in and out. So that's just an example. If the original function is weaving in and out and has an infinite number of zeros, then the derivative is going to have an infinite number of zeros. Great. All right.